This is a presentation on some of the big questions in lunar science. I updated it a little bit since last year, but a lot of it is the same. And so if there's something new and exciting that you've come across that might not be in these slides, we can talk about it afterwards, because I just did a little bit of light updating. But yeah, my name's Parvathy. I am a planetary scientist at the Johns Hopkins Applied Physics Lab, APL, in Laurel, Maryland. I am part of the teams for 2 lunar spacecraft, one which is currently orbiting the moon, the Lunar Reconnaissance Orbiter, and the other which is planning to travel to the moon in 2024, that's Viper. You might have heard of SERVI, the Solar System Exploration Research Virtual Institute, which consists of teams that are spread across the US. The ExMASS program is partly supported by SERVI, and I'm a member of a couple of SERVI teams as well. Okay, so this presentation is mainly an introduction, just an introduction to some of the big open questions in lunar science, and there are a lot of them. And we could go into them in a fine level of detail, and many of you will likely do that during the course of your research projects. But for the purposes of this presentation, I'm aiming to cover a lot of stuff and go into maybe medium level detail on those. And so some of those questions might be things that you do a deep dive and focus on in greater detail on in your research projects. So one goal for today is for me to give you a bit of an introduction. And the second goal is to do something that you will be doing a lot of over the course of the semester, which is asking questions. There is absolutely no such thing as a stupid question. I always say that. I've never heard anyone ask a stupid question yet. And so this is as good a place to start as any. You will be asking yourselves lots of questions and trying to answer them soon. So another goal for this evening, or I guess afternoon, if you're, well, it's evening in Oregon as well. But another goal for today is to start exercising your questioning muscles and think of, you know, what prompts your curiosity here? What questions do you have? So topics in this presentation, the moon obviously features heavily. And so this is an introduction not just to the moon, but I've also tried to include some information on the various different ways of doing lunar science. So one of the great things about lunar science, planetary science more generally, is that there are almost as many different ways of doing science as there are scientists. So depending on, you know, whether you like writing code on your computer, like I do a lot of, whether you like going out into the field and exploring lava tubes, or if you like playing with chemicals or rocks in a laboratory. There are lots of different ways of doing lunar science, and so I've tried to touch on at least some of them here. A lot of the material for this presentation is inspired by and drawn from a couple of these important reports. So these are Advancing Science of the Moon is, you know, maybe something like 30 pages. The Planetary Science and Astrobiology Decadal Survey is almost 700 pages, so you don't want to go and read the whole thing. But I'll share the slides afterwards, and I've included links to those reports in case, you know, you want to dive deeper into some of the things that I'll talk about today. There is a lot of information in this presentation, and it's almost certainly going to include, you know, either words or ideas that you haven't yet thought a lot about. That's intended, that's expected. And so if something like that comes up, make a note of it. We'll talk more about those at the end. Feel free to also drop questions in the chat. I'll try and keep an eye on it, but I won't focus on it too much until we sort of do the grand tour. So the main motivation for scientific study of the moon really lies in the fact that, you know, the moon is our neighbor. We live not just on Earth, we live in the Earth-Moon system. And this is a direct quote from one of those reports I meant, well, not one of those reports, another report that I didn't mention. So the quote is that, you know, above all, the moon is a witness to 4.5 billion years of solar system history. And there's nowhere else in the solar system that we can see back with such clarity to the time when Earth and the other terrestrial planets were formed and life emerged on Earth. And that really is sort of the cornerstone motivation for studying the moon. It's our neighbor, and the story of the moon is also the story of us. And this is sort of like the big picture overview of that story. So our current best guess for how the moon formed is that it was formed around 4.5 billion years ago in a giant impact. So an object slightly smaller than the proto-Earth collided with the proto-Earth fairly energetically. The debris from that collision was thrown into orbit around the Earth, and it coalesced to form the moon. Over the next many billions of years, the moon and the Earth were bombarded by comets and asteroids. So all of the leftover rocky and icy building blocks of the solar system pelted the lunar surface, and they also pelted Earth at the same time. And on the moon and in some places on Earth, the scars are kind of smoothed out on Earth by water and winds. But you can see all over the face of the moon craters left by those comet and asteroid impacts. Over time, those impacts became smaller and less frequent, but they do still happen today. One of the things I'll talk about briefly is that we are still observing new impact craters being formed on the moon, even today. From the other major geological process that has shaped the moon that we see today is volcanism. So from about 3.8 to around 1 billion years ago. And so for context, this is when the oceans are forming on Earth, and when the organisms that formed the earliest fossils that we see today were swimming around in those oceans. During that time, the moon underwent several episodes of really widespread global volcanism. And so when you look up at the moon today and you see those dark regions, those maria, those are those ancient solidified lava fields, which tend to show up as a slightly darker rocks. Once upon a time, those were huge molten pools of lava, and not all at the same time. Sometimes they would. So if you imagine yourself on this early Earth, even before the dinosaurs, looking up at the moon would have been closer to Earth for one thing, but you might have occasionally seen these bubbling molten pools of lava across large parts of the lunar surface. Volcanism came to an end about 1 billion years ago, we think. And if you look at the moon today, you might think that it's a very quiet world. For the most part, it is, but it is still an active and very dynamic world. Smaller impacts do happen today, ranging from things that are, maybe basketball size or backpack sized, to those that are even smaller, micrometeoroids. All of those micrometeoroids that form shooting stars when they burn up in Earth's atmosphere go straight through and strike the surface of the moon and churn it up even today. And then there's also the solar wind, which is the stream of hydrogen and helium and other gases that flows outward from the sun and touch all rocky bodies in the solar system, especially those with very thin atmospheres like the moon. So even today, the moon is geologically active. There are processes that are shaping the surface of the moon even today, and sometimes we can observe them in unexpected and interesting ways. So a lot of the work that you might end up doing in your research projects might involve working with remote sensing data. So these are observations that are collected sometimes from, some types of remote sensing data could be collected from ground-based telescopes on Earth, or from airborne telescopes that fly above the troposphere, above all the weather that's happening on our atmosphere. But a lot of remote sensing data comes from lunar orbit, from spacecraft that have left Earth, flown to the moon, and spent sometimes many, many years orbiting the moon and looking at it through different kinds of eyes. So there are a lot of different kinds of remote sensing data, and nearly all of them involve sensing some kind of electromagnetic radiation. So if you haven't taken an electromagnetism class yet, you probably will at some point. But electromagnetic radiation, the electromagnetic spectrum is an extension of the light that we can see with our eyes, which falls, somewhere in this wavelength of around 400 to 700 nanometers. At longer wavelengths, you have infrared, which is what we sense as heat. You have the ultraviolet, which you can see with some kinds of torches. It's the stuff that gives you sunburn. And then you have X-rays and gamma rays, which you might have heard of. You have microwaves and radio waves, which you've almost certainly heard of. All of those are different kinds of electromagnetic radiation that we can view the moon at all of those wavelengths. And over the years, the moon has been observed at almost all of these wavelengths that are listed here. You can see some of those data sets on various tools. One of the ones that you should check out if you haven't come across already, and you might end up on this at some point, is the LROC Quick Map tool, which is a great resource for visualizing some of the different data sets that have been acquired from spacecraft in lunar orbit. So that's not the only kind of data, though, when it comes to the moon. So you can observe the moon at different wavelengths. So that's like, swapping out your regular eyes for a pair of infrared spectacles or for a pair of ultraviolet spectacles. But there are other things you can measure that don't necessarily involve looking at the surface in a different way. So for instance, you can measure forces. A while ago, there was a pair of twin spacecraft called Grail that orbited the moon and measured how they were tugged as they moved over the surface of the moon. And they used that to map the gravity of the moon, which can vary just a little bit. So the spacecraft were sort of moving along in orbit, and they were very sensitive to how much the moon was pulling at them. So you can measure forces like gravity or magnetic fields. You can also measure particles. So for instance, I briefly mentioned the solar wind, which is that stream of hydrogen, mostly hydrogen, that flows out from the sun, interacts with the surface of the moon. You can measure the solar wind. You can measure the molecules that are created when the solar wind interacts with other atoms and molecules in lunar rock. So you can measure particles, you can measure molecules in the moon's very thin atmosphere. Sometimes those are charged particles, in which case they're ions rather than molecules. And so you'll get very familiar with at least some forms of remote sensing data. And so all I wanted to say for now was to just give you some sort of guiding questions to ask when you're working with any kind of remote sensing data. I think that the first thing to understand is, and I think this is always a really useful thing to understand when you're working with a data set, but ask yourself, what is the instrument measuring? What do the colors that you see in a map, what do they really mean? And if you get that basic understanding, it's sort of rewarding in itself. It's a cool thing to understand what you're looking at, but it's also useful when it comes to drawing scientific conclusions from that data. Something that's sometimes useful to know is whether something is an active or passive technique. The difference between those: in passive techniques, you are typically looking at reflected solar radiation. In an active technique, you might be doing something like shining a laser at the surface of the moon, like like one of the instruments on board the Lunar Reconnaissance Orbiter does. So an active remote sensing technique is when you're bringing your own source of energy. And so things like laser altimetry, when you come across it, which is shining a laser at the moon and measuring how long it takes to come back, or radar, when you beam radio waves at the moon and see how they're reflected. Those are active remote sensing techniques. It's also often important to know the resolution of the data. When you look at a map, what is how big is a pixel in that map? How far can you zoom in before you see just a box? When you're working with spectroscopic data, you might want to think about spectral resolution. There are also changes that occur on the moon over time. And so sometimes you might want to know the time resolution of data sets. And it's good to have at least some sense of how uncertain the data are. Some things are more, some techniques are more precise due to the nature of those measurements than other techniques. So that's something else you want to file away in the back of your head. Something else that's important is the depth to which different techniques are sensitive to. So one of the reasons why it's so interesting to look at the moon in these different wavelengths is that these different wavelengths are usually sensitive to structures on the same scale as the wavelength. So what that means is that if you're looking at the moon, for instance, in the ultraviolet, where you have wavelengths of a few hundreds of nanometers, if you look at the lunar surface in the ultraviolet, then you're sensitive to features on the scale of the grains that make up the top hundreds of nanometers of the lunar surface. If you go to much longer wavelengths, so if you're looking at the moon in terms of radio waves, then because those radio waves have a longer wavelength, you're sometimes also seeing deeper into the lunar surface, because and so radar waves can tell you information such about things such as buried subsurface rocks, because generally the wavelength of the radiation with which you're seeing the lunar surface, it also determines how deep below the surface you're seeing, and the scale of the structure that you're seeing. And that may not make sense at the moment, but it's, you know, stored away in the back of your head, and it might come in handy at some point down the line. There are many different ways to be a planetary or lunar scientist, and I think that's one of the best things about planetary science. And so just to give you a brief idea of some of those techniques, you can spend your time doing data analysis, looking at maps of the moon at some of those different wavelengths. You can do lab experiments where you investigate samples under the microscope, or you set up neat experiments like this impact experiment that Angela and Tarek here are doing. You can measure things. You can also use computer simulations, such as this one, which is by Dr. Robin Canup. And so this is one of the simulations that she did almost 20 years ago of how the moon may have been formed. And so you start with an object colliding with the proto-Earth, you get all of this debris, and then over time, if you write computer code to model the physics and math and chemistry of that, you can end up with a little moon that you see here. So all of these ways of doing science are equally valuable. And I think that the beauty of planetary science is that it brings all of them together. Some people do more than one of these things. Some people focus on just one technique. And those are all valid and good and enjoyable ways of doing science. So getting into some of our science themes, the first theme that I wanted to touch on is that of solar system bombardment. So one of the most important pieces of knowledge that the moon has given us is about the timing of solar system events. The moon is one of the few solar system objects from which we have samples. We have samples from some other solar, some other solar system objects in the form of meteorites from Mars and the asteroid belt that reach us. But the moon is the only place where we've been and collected samples from carefully chosen regions. One of the magical things you can do with samples, if you have a piece of rock in the lab, you can look at the elements that make it up and figure out how old the rock is. So that's sort of like it's a complicated but simple task. You're determining how old a rock is, but then that's like a key that unlocks the timing of almost everything that's happened in the solar system. And we rely on rocks returned from the lunar surface to pin down the timing of key solar system events. So in that timeline that I showed you a few slides ago, how do we know if something happened 3.8 or billion years ago or 100 million years ago? A lot of it is from lunar rocks. And even when we look at other planetary bodies, we rely on knowledge we have from our study of the moon to figure out things like when Mars had running water. And so the moon is sort of like the clock with which we date solar system events. So this is a map of lunar craters, which record the timing of one of the most important and widespread solar system processes, which is bombardment by asteroids and comets. And so there are craters that we can see, which are marked in sort of pink or magenta here, and craters that are buried and tend to be older, like some of these yellow ones. And we can see the buried craters using gravity and topographic data. And so some sort of middle level of detail questions that you might want to dig into at some point are, and these are things that people are actively thinking about. Questions such as, what are the best places to go if you want to know the timing of important events in lunar history? People are very interested in questions like, what is the oldest impact that happened on the moon, and what could that tell us about the early state of the moon? Another interesting one is, what is the geologic context of existing lunar samples? So we have lunar samples from a number of locations, but it's important to know their geologic context. So for instance, the Apollo astronauts collected samples from a variety of different regions, but later analysis found that many of those samples might have been generated by the impact that formed this big impact basin marked with an I. That's the Imbrium Basin. So people sort of looked more closely at maps and other kinds of data and figured out that, hey, some of those samples that were collected from quite far away may actually have come from this big impact crater. So that's the geological context, understanding the nature of locations from which we have lunar samples. I've included these little mission spotlights, and these are hyperlinks to some of their mission pages. So these are either upcoming, past, or present missions that are relevant to some of these questions. So for instance, Endurance A is a mission concept that was studied recently. It's not actually an officially approved mission yet, but it's a mission concept that would explore one of the oldest, largest basins on the moon in order to help us better understand the timing of some of the really early large impacts that shaped the moon and potentially the Earth as well. Then there is the lunar interior. So the moon, we think, formed hot in a giant impact. It initially had a global magma ocean. Over time, heat radiated to space from the interior of the moon, and we think the interior of the moon gradually cooled. But there's a lot about the lunar interior that we still don't know. We're not still quite sure. Does the moon have a core like Earth? How big is that core? Is some of that core molten? Was it ever molten? When did it solidify? So the lunar surface, you can spend a lifetime looking at the lunar surface, but the lunar interior has its own set of mysteries, and those mysteries sometimes manifest in really interesting ways. So for instance, just like we have earthquakes on Earth, the moon has moonquakes. And so that's one area of active study, identifying where moonquakes originate from and originate within the interior of the moon, and also what causes them. Is it due to, so the moon doesn't have tectonic plates like the Earth does. So on Earth, earthquakes tend to have their epicenters at the edges where those continental plates collide. The moon doesn't have tectonic plates, but what causes moonquakes? Some of them might be caused by impacts that sort of make the moon ring like a bell. Some of them might be caused by deep rocks settling against each other and maybe collapsing in a little bit deep within the interior of the moon. So there are moonquakes. The moon is still radiating heat to space. So there's a lot of interest in, and so measuring the amount of heat coming from the deep interior of the moon can tell us something about, how quickly did it cool? Is it still cooling? How fast is it cooling? When did the interior of the moon solidify? Magnetic fields. Unlike, one of the big differences between the Earth and the moon is that the moon doesn't have a big global magnetic field like you have on Earth. But there are patches of the lunar surface, and we'll talk a little bit more about those later on, but there are patches of the lunar surface where you have local magnetic fields, almost as if there's a big magnet buried somewhere beneath the surface, but just in one small location. And those magnetic fields are related to what's going on below the surface that you can see. There are also, although the moon doesn't have tectonic plates, it does have what are referred to as tectonic features, like some of these wrinkle ridges that you can see, which really are sort of ridges that look a little wrinkly. Those are formed when the moon cools and contracts, and that process of cooling and contraction, or in some cases expansion, can lead to cracks. So kind of like a pie crust, or I don't do much baking, so this might show, but kind of like what I imagine a pie crust, or like the crust of a loaf of bread does, as it as it cools or is heated up. Or this baking analogy was a very bad way to go, because I don't know what I'm talking about. But questions to explore. What does the surface of the moon tell us about what's going on in the deep interior? How did the moon's magnetic field change over time? We think once upon a time, the moon might have had a magnetic field like Earth. Where did it go? How do we find out? And then, is the moon tectonically active in the present day? Are some of these wrinkle ridges still kind of cracking and shaking and heaving even in the present day? There's some work that suggests that in some regions you might have some active tectonism, that the moon might still be wrinkling and cracking under the stress of what's going on deep under the surface. One of the upcoming missions that's going to explore this, I think it's set to launch a few years from now, 2024, if I'm not mistaken, the Far Side Seismic Suite. As you might guess, is a suite of scientific instruments that is going to the far side of the moon, so the side that we don't see from Earth. And it's a seismic suite, so it's going to watch for some of these moonquakes, these deep moonquakes or these shallow moonquakes, and try and understand something about the interior of the moon based on measuring some of those quakes. That's the interior, and then there's the crust. So the crust is sort of like the thin crust of the moon, so it's relatively thin compared to the depth of the interior. But the crust is the pages on which all of the other stories that have happened on the moon are written. So the crust is lunar rocks of many different kinds. You can look at their composition. You can look at spectral data, which is measured by spectroscopic instruments that tell you how those rocks reflect light at different wavelengths, which again tells you something about what those rocks are made up of. And so, for instance, this is a map of composition overlaid on a map of lunar terrain. And so the colors here tell you whether a region has rocks that are rich in iron, or regions that are rich in silica, which is the main constituent of sand on Earth. And so one thing you might notice is that the iron-rich parts of the moon tend to be the regions that were associated with volcanic activity. So it's those vast volcanic plains that look dark to the eye that also tend to be iron rich. And so there's interesting information there. The colors here, if you want to go into them in a little bit more detail. So these are telling you something about the location of a certain spectroscopic feature. So if you look at how the moon reflects light with a wavelength between something like 6 to 10 microns, you'll notice that if you sort of look at, so if you step through the wavelengths and you're like, how much is the moon reflecting at this wavelength? How about at this wavelength, at this wavelength, this wavelength? As you step through the wavelengths, you'll notice that there's one wavelength at which you see a little bit more light being, and in this case, not actually reflected, being radiated as heat from the lunar surface. And so depending on whether more heat is emitted at a longer wavelength or a shorter wavelength, you can tell what the rocks are made of. And this took me years to understand, and I'm trying to explain it to you in a minute. So it is okay if this makes sense. If this doesn't make, it's okay if it makes sense, but it's also okay if it doesn't make sense, and we can talk about it more. And I think almost every single bullet point here, you can spend a whole lifetime understanding this stuff. But composition of the crust is a particularly interesting topic because there are some regions that have compositions that you might not expect. So for instance, while most volcanic regions tend to be very iron rich, there are some regions which are kind of hard to see on this big map. There are some regions where you can tell that volcanism happened because they have domes and other volcanic features, but they tend to be unusually silica rich. What's going on with that? I thought all volcanic fields or all volcanic rock should be iron rich. A mission that is going to investigate that is Lunar, which is led by another former ExMASS advisor, Dr. Kerry Donaldson-Hanna at the University of Central Florida. Lunar is going to go to one of those unusual volcanic regions and learn more about why some volcanic regions are not so iron rich. Then, if we move to the poles of the moon, this is also related to the question of composition. But one thing that you might have noticed is that most of the conversation so far has been about rocks, things that are really pretty solid. The moon also has a volatile cycle. So generally, when we talk about materials in the solar system, we talk about refractory materials, which are like the rocks that are really hard to melt. And then there are the volatiles, which are the things that form our atmospheres and oceans and ice caps on Earth. So there are things like water or nitrogen, carbon dioxide, the things that are usually present either as ices or as atmospheric gases. The rocks on the lunar surface, as we've talked about a little bit, the rocks on the lunar surface carry a certain kind of geological record. So you can visit certain craters to figure out the age of these impact events. You can look at whether there were periods of time when the moon was being hit by a lot of rocks. Those craters and those volcanic plains, the moon rocks record geology and record geologic time in a certain way. But there's another record that's held in very cold, very dark craters that are often referred to as permanently shattered regions, or PSRs. That's an abbreviation you might come across a lot because people are talking about PSRs a lot of the time. So these are cold, dark craters near the lunar poles. Some of them are outlined in the circles here. And so so for the most part, the moon is pretty dry. It's certainly much drier than Earth, where we're surrounded by this, nice, comforting atmosphere. We have oceans and ice caps. The moon, for the most part, is fairly dry. But it's only in these cold, dark craters near the lunar poles that ices have a chance of existing. And we have data from several spacecraft that suggest that, there is indeed ice in some of these craters. So we've looked at the moon at all of these different wavelengths. We've looked at reflected sunlight. We've tried to do neutron spectroscopy. We've looked at the moon in infrared and ultraviolet light, and we've beamed radar and looks at what comes back. And a lot of those things tell us that there's ice in some of these cold, dark craters on the moon. And one of the most intriguing things about that ice is that it's very old. It's likely much older than, for instance, even the deepest ice in some of those deep ice cores that you can take from the Arctic or Antarctic polar caps on Earth. And that ancient ice is interesting for some of the reasons that ancient rocks are interesting, because by looking at those ancient ices, we hope that you can investigate things like how water and some of the other important ingredients of life reached our own planet. So for instance, if we could travel to one of these deep shattered craters, the ices that we find there might tell a story similar to the stories that you see recorded in, for instance, layers of rock in the Grand Canyon, or if you've ever seen any of those rock faces, which have these different layers of rock. We think in some of these regions, there might be layers of ice that tell you about the early history of how water and some of these other things that are so important to life, many of which tend to be what we call volatile materials. How do those reach the inner solar system? And so questions that are actively being explored are, what is the origin and the age of some of those polar volatiles? How are they distributed? Because we don't always see water everywhere where it's cold enough. There are things we don't fully understand about where are the best places to look if we want to find water on the moon. And then how do, because some of those ices are really old, how have they changed over time? What happens to ice if it's exposed to billions of years of solar system history? How do impacts break up ice and mix it into the regolith? What kind of chemistry happens in some of those cold, dark craters? There are several missions that are studying polar volatiles in various different ways. Viper is the rover that I'm involved with that's going to travel to right about here in 2024. Viper is going to a region on the rim of Nabile crater, which is one of the big cold dark craters. There are some tiny little cold dark craters that you can't see here, and Viper is going to spend some time wading into and out of those and seeing what the ice looks like really close up. And then there's Lunar Trailblazer, which is a mission that's launching a little earlier, maybe in 2023, that's going to map some of these, some of the water on the moon from orbit, so that we have this big global view of where water is and how it's distributed, how it changes with time, all of that good stuff. Volcanism, we talked about volcanism a little bit, but it's one of the main processes that has affected the moon over time. And there are so many volcanic features. So there are lava tubes and pits, which some of you know more about than me. Those are literally pits in some of these volcanic plains, and where you can, if you look at images that are taken at an angle, you can actually see layers where lava flows have flowed over time and built up. There are also very strange volcanic features like this one. This is Aina, which is an imp or an irregular mare patch. We really have no idea what this is. We don't see it on Earth, but you can see it's sort of unusually blobby with some unusually smooth and smooth areas interspersed with some rougher, brighter areas. We really don't know what it is, but we think it's a very young volcanic feature. And imps are a bit of an enigma. We don't really understand what these are. There are also volcanic deposits. So when a volcano erupts, you're probably thinking ash. On the moon, during volcanic eruptions, you often end up creating fountains of glass beads that are distributed over large distances. So if you have volcanic gases coming up from a vent like this one that you can see in the center of this this figure, volcanic those gases and that magma that's coming up from the surface cools very quickly, so quickly that some of it becomes glass, and so you have these vast debris fields that are created as a result of these volcanic eruptions. We call those pyroclastic deposits, and the colors here actually show you how much water is in some of those volcanic glasses. So apart from those cold dark craters near the poles, another place where we think there's some water present on the moon is near these pyroclastic deposits, and understanding that is also something that folks are working towards. So for instance here's our volcanic vent, and you might notice that so red here means that something contains more water than something that's blue. And so you can see that areas closer to the vent seem to be wetter. They seem to contain more H2O or OH in chemical form than regions that are further away. Does that mean that the magma that erupted from this vent was water rich? Those are some interesting questions to investigate. And cryptomare, I don't have a photo of cryptomare here. Cryptomare are mare, which are volcanic plains that are buried under layers of regolith, and so they don't look quite as dark as the regular mare, but you can tell that there's something cryptic beneath the surface there. So crypto from, I believe, the Latin hidden. So these are hidden mare that are hidden beneath dust and rocky regolith. Big open questions. When did lunar volcanism begin and end? Are these irregular mare patches some of the most recent volcanic features? Are they some of the youngest? And how did the composition and eruption style of lavas change over time? Were magmas always water rich, like the one that might have formed this pyroclastic deposit? How did things change over the billions of years over which volcanism was active? And so 3 of these images are from the LRO mission. This is from the Chandrayaan-1 spacecraft, which was operated by the Indian Space Agency shortly before LRO. They overlapped a little bit. LRO is the Lunar Reconnaissance Orbiter, which you'll hear lots about in the months to come. The other major process that has affected the lunar surface is impact cratering. Here's a patch of the lunar surface in, 2010. Here it is a few years later, and you can see that a new impact crater has formed. Impact cratering is still happening. We can see them through camera images like this one. We can also see the effect that they leave in the infrared. So this is a map that's derived from temperature measurements of the lunar surface. And so you can see that, I'm not sure if it's the same crater, but in the center is this little new crater that formed fairly recently. And you can see that, it's affected the region around it to quite a large distance. So everything that's sort of blue indicates a region that's been affected by that crater. Craters can be really small, like these ones, which we observed today. They can also be massive. So for instance, here are the locations of regions that have been mapped as light plains. We see these, what we call these light plains, all around the moon. And for a long time, it was a little bit of a mystery. How were these light plains formed? A colleague of mine at APL, Heather Meyer, mapped those light plains and found that they seem to extend radially outward from this huge crater, Oriental. And so what Heather inferred from her mapping is that these light plains that stretch all the way, all across the moon, formed somehow as a result of that massive basin-forming impact. So there are craters of various sizes and ages. How did they change the lunar surface? Then there is the regolith. So the regolith is the rocky debris that covers the lunar surface. It's affected by processes such as micrometeoroid bombardment and solar wind interactions, which we talked about a little bit. And the moon is sort of like a natural laboratory where we can understand these processes. So these happen on asteroids and on all the rocky so-called airless bodies of the solar system. And the moon is an ideal lab to understand how things like micrometeoroids and solar wind change the lunar surface, and they do in very observable ways. Micrometeoroids and the solar wind can darken the lunar surface. That's why younger craters tend to be brighter than older craters. And then I promised you a little more about those magnetic fields. Lunar swirls. This is one of those lunar swirls, Reiner Gamma. The black and white image is real. The colors, so the orange here shows the invisible magnetic field that is present at this region. The blue streaks are a visualization of the solar wind. And what this animation that you can go back and dig more into later if interested. What this animation is showing is that the magnetic field affects the direction of the solar wind, and that's what gives you these, or at least that's what we think contributes to forming these dark and light swirly patterns over the surface of the moon. A mission led by one of my favorite people, Dr. Dave Blewett at APL, Lunar Vertex. Dave is leading the Lunar Vertex mission, which will travel to this lunar swirl, which is referred to as Rhino Gamma, and investigate whether this really is what's happening. Is our theory correct that magnetic fields deflect solar wind ions to form dark and light patterns on the lunar surface? And Rhino Gamma, you can actually see Rhino Gamma from Earth. So if you try taking a photo of the moon through a telescope, or even with your phone or through binoculars, see if you can find Rhino Gamma, because you can see it. A friend of mine sent me a photo of the moon that she took with her phone the other day, and I was like, oh, look, there's Rhino Gamma. But the questions there are, how do micrometeoroids, solar wind, other processes affect the lunar surface? How do those processes vary with location and time? Things can be different depending on, for instance, whether they're magnetic fields, like it swirls. It can also depend on time. So at different periods during the month, the moon is exposed to a different space environment. Micrometeoroid showers and the solar wind, the strength of the solar wind all vary with time. So some of these things change over timescales that we can observe. And then last but not least, above the regolith, enveloping the moon, there's dust, there's plasma, and there are volatiles, not just in craters near the poles, there are also volatile gases in the exosphere. And so that dust, those volatiles, that plasma, those are how the moon responds to the space environment. There is an environment in space. We call it the space environment. And so all of these things respond in interesting ways. So for instance, dust is created whenever micrometeoroids hit the moon. Sometimes they release volatiles as well. We can see that dust. This is an image of, this is derived from measurements of dust in lunar orbit by a mission called LADEE, the Lunar Atmosphere, Dust and Exosphere Explorer, or something completely different. All I can guarantee is that the L stands for lunar and the D stands for dust, and exosphere is in here somewhere. LADEE measured dust density around the moon, the lunar dust cloud, and saw that sometimes it changed. For instance, when you had a micrometeoroid shower. You can also map volatiles beyond the lunar poles from lunar orbit. So this is a map that shows you one particular volatile, which is hydroxyl, and how it is spread across the lunar surface. And so this is so the idea here, and this is me putting too much information into a slide. This map is interesting because the hydroxyl, the OH that we see in these colored regions, is created when hydrogen, so that's the H from the solar wind, interacts with oxygen in lunar rocks. And so this is a sign of what we call space weathering, which is what happens to a rock when you expose it to space. On Earth, when we talk about weathering, we're usually talking about things like erosion by winds and water. On Earth, so on the moon, you have space weathering, which operates in different ways. Lots of open questions there as well. And I will send you the slides afterwards. So don't worry if I'm going too quickly over stuff. But some closing thoughts. Most important thing, everything you need to do good science is something you can learn. No one is born with this magic ability to do planetary science. Every single skill or way of thinking that you need to do good science is something that you can learn. How to write scientific papers, how to read scientific papers, almost every single task you can think of is something that's a learnable skill and that you can always learn to do better as well. You'll be working with advisors, some tips. There's no such thing as a bad question, so ask them. One of the nice things about most scientists is that if they don't know the answer to something, they'll try and find out. Sometimes that involves finding someone else who knows the answer. So don't feel bad about asking a question that your advisor doesn't know the answer to. They'll find someone who does, and everyone will learn something in the process. If you're interested in doing something, don't rule it out because it seems too complicated, or it seems like, you might need some kind of equipment or technique that's too complicated. Look into it, because some of these things, there are ways to do these things that might be more straightforward than you might think. Some philosophical thoughts on being a scientist that I won't go into in too much detail, but but in brief, it's okay if you end up with more questions than answers at the end of your work. That's great. That's the kind of science that I like best. Some people find it frustrating if you end up with more questions than answers, but I like it. So do lots of people. Planetary science is super cool, but it can also be really boring at times. So if you find yourself really, really bored, don't automatically rule out this as something that's not for you. Everyone who does planetary science, sometimes we sound super excited about it, but trust me, there are many, many days when we find this extremely boring or extremely frustrating, and we'd much rather do something else. It doesn't mean you're doing it wrong. That's part of the process. And then, science is not just about the solar system. It's also a way to learn about what kind of things you like doing and how you work with other people and how other people think. And I think, the more time I spend doing science, the more I find that, the people who do this work are just as interesting, if not more interesting than the objects we study. So lean into that and enjoy that part of it as well. Very last slide that I added 2 minutes before I joined this call. APL does many exciting things. It's a great place to work. This has nothing to do with the moon, but check out dart.jhuapl.edu. DART is a mission to test whether we can deflect a tiny little asteroid as practice for potentially doing the same thing if we find. So DART is going to see if it can change the orbit of an asteroid that poses no threat to Earth. But the idea is that, if someday we do find an asteroid that's headed towards Earth and ready to make one of those huge craters, this might be a way to deflect it. And if that very rushed explanation of what the DART mission is makes no sense at all, do check out dart.jhuapl.edu. DART is the first planetary defense test mission. It's going to intentionally impact an asteroid, intentionally sort of, give it a little fist bump on Monday, the 26th of September. So obligatory little APL ad there, because everyone I work with is very excited about this, and they've gotten me excited about this as well, even though it's not something I work on directly. And so with that, I know I used up most of our hour. I'm hoping we still have time for a few questions, and I will share the slides with Andy. And if you think of other questions later, Andy has my email, so feel free to reach out to me directly. I think my email is also on the Zoom invite that you might have. I'll also put it in the chat. But feel free to reach out later if you have more questions as well, because I know I went kind of long here, as I tend to do.
Well, there's just so many cool things to talk about, right? I mean, how do you narrow it down, right?
Yeah.
So as you all, yes, say hi. So as you all can see, lunar science, there's a lot going on. There's a lot of potential things to investigate. The moon is just, it may not be what you thought it was, which is just pretty cool. And I would also echo Parvathy's statement about just the people that do planetary science. They are pretty cool. Now when I went to grad school at the University of Arizona, I started as kind of spending time around astronomers, astrophysicists. And then I wound up spending most of my time though around planetary scientists. And I'll just let you decide which one I much prefer to spend time with. Now that's just one example, but it's an example. So anyway, anybody have any questions that popped in your mind while watching this? I know it was a lot, but we recorded it, so you can certainly go back. Feel free to unmute your mic or raise your hand, or
Daddy,
you even use a chat box.
Daddy,
That's fine.
is that recording?
It is recording.
But why are you talking to me?
We recorded you.
Careful. No? Okay. Well, no
I have
worries.
a question.
Oh.
Just a second. First, I'd like to thank everyone of Dr. Prem. That was an amazing presentation, and you made it so accessible and clear, and sparks our curiosity. And I can't wait for my students, a bunch of whom are here today, to start their work. Could you please speak to some of the type of data that exists for the different types of questions, such as, for example, one example would be for the magnetic field of the moon. What type of data would we, would the students would be looking at? And how about also regarding the craters, the history of the craters, what type of data is available to look at? Thank you.
Yeah, that's a great question. So I'm going to share my screen really quick. So this is that LROC Quick Map site that I pulled up. And so one of the things you can do, and Andy or your advisors can refresh your memory on this if you forget exactly what I clicked. I don't really know what I'm doing here either, but there are a number of different data sets in this, and we typically call them layers. So when people are talking about layers in Quick Map, they're talking about different kinds of data. And so, for instance, and there are ways to search this data and identify what you're looking for. But for instance, if you wanted to look at magnetic fields, I happen to know from hanging out with Dave Blewett that Lunar Prospector was one of the spacecraft that collected data about the magnetic field of the moon. So I can scroll down to Lunar Prospector. I want to see a magnetic field map, and so for some reason it's not letting me rotate my. Let me go to a different. Let's do a lunar globe. And now my computer is going to freeze as punishment for trying to show off in real time. Right, let's do something less extensive there. Oh no, it went away, and then I see this is sort of like this is life as a planetary scientist. But you saw it for a minute there. But you can basically. Here we go. So this is the map of magnetic field strength across the lunar surface. And there are, it's really fun to just click around and see what's available. But that's a really great question. And so there's all kinds of different data. So there's a lot of camera images, which are kind of like the most intuitive thing. It's kind of what you would see. But then there's ultraviolet data, and almost everything I mentioned exists as a data set somewhere. And I see Ella has a question in the chat. Do the locations of permanent shadowed regions change over time? Did the ice that's there today get to the PSRs initially in the form of liquid water? So those are both excellent questions. The first one, do the locations change over time? That's actually a big open question too. And that's one that you guys could investigate. There are reasons to think that they might have changed over time. I won't go down that rabbit hole, staying away from that rabbit hole, but there is research that suggests that some of those locations may have changed over time. And when I say over time, so the permanently shadowed regions that we see today, we think those have existed for almost 2 billion years. But before that, we think that, the moon may have tilted and wobbled a little bit, so that some regions that are shadowed today weren't previously in shadow, and some regions that used to be shadowed are no longer in shadow. That's a really interesting question to investigate. Did the ice that's there today get to the PSRs in the form of liquid water? We think that it probably got to the PSRs in the form of water vapor in a gaseous form. So we think it sort of went directly from steam to ice without becoming liquid in between. And the reason for that is that for liquid water to exist, you need to have a certain amount of atmospheric pressure. So on places like the moon, which have very thin atmospheres, water tends to go from vapor to ice without the liquid phase in between, because there isn't enough atmospheric pressure sort of helping water droplets stay together. But those are really good questions.